Hello everyone, welcome to Unit 8 Ultimate Guide on Fluids. We're going to be discussing everything for Unit 8 for AP Physics 1. We start off learning about internal structure and density and then move into pressure. And then we sort of use those different concepts to compare fluids and Newton's laws and then talk about some conservation laws with respect to fluids. So this is actually a newer unit of AP Physics. When I took it, it was not there. So it's kind of interesting. Very different from all the other units in my opinion. Um, but yeah, so feel free to jump around as you need. The timestamps will be in description. So let's get started. So we'll go through the basic states of matter. So starting with solid, it has a definite shape and definite volume. Now you've probably heard this many times. So what does that kind of look like when we're talking about the structure of a solid? It's tightly packed molecules. Let's say we had like a cube structure that are all tightly together. No matter what container it's in, it's going to have the same shape and the same volume. Now, liquid does not have a definite shape, but it does have a definite volume. And so if you put a liquid in a cup, then the volume is going to be the same whether you put it in a cup like this or maybe a taller cup. It's going to have the same amount of volume, but the shape is different. And so when we talk about this ideal fluid, it basically means that it's made up of molecules. It's not viscous. It doesn't have like fiber type structures, and it's incompressible. And so what incompressible means is that if we had this fluid here, let's say there's like molecules, and we have like a piston pushing down. Even if we applied a force, the volume would not change and the piston would not go downwards, and that's what incompressible means. Okay, and so gases have no shape or volume. So let's say we put a gas in like a container like this, and it has some molecules in it. It's going to depend on the container how much volume this gas takes up and the shape it takes, which means a gas is compressible. So let's say we had a piston on a container like this, and we pushed it down to, let's say, here. Now the same amount of gas is going to be in here, but it's going to be pressed to a different shape and a different volume. And we'll denote this difference by the difference in pressure, and we'll talk about more about pressure in the next video. But in this video, let's talk about density, which mainly when we're talking about density, we're talking about solids and liquids. So the density is given by this equation here. This is called rho, which is what the symbol we use for density, and it's the mass over the volume. And so if we had, let's say, like a cup like this, and we had maybe like some thick liquid at the bottom, and then maybe there's like a lighter liquid up here, and then we have like a ping pong ball on the top. These are separated by their densities. So this bottom one has the highest density because it is at the bottom, so it has the most mass per unit of volume. And the least mass per unit volume is the ping pong ball at the top. Okay, so let's look at an example using density. So water has a density of 1 gram per milliliter. A block with a volume of 8 milliliters is placed in water. How much mass can the block have and still float on the water? Okay, so let's write out what we know. We know the density of water is 1 gram per milliliter. And we have a block that has a volume of 8 milliliters. Okay, how much mass can the block have and still float? So we want to find the mass of the block where it's still floating. So let's draw this out. We have a cup here, and there's water and there's a block. Now we know the block's volume, but we want to know the mass while it's still floating before it sinks, which means that the density of the block must be less than or equal to the density of the water. Okay, and so for our case, we want to find the maximum it can have before it sinks, so we want to know when these densities are equal. That'll give us that max mass. So we know the density is the mass of the block over the volume of the block must equal this density of water, which they gave us, and which is known. And so now we can multiply the volume to the other side and get the mass of the block equals the density of the water times the volume of the block, and plug in our known variables, 1 grams per milliliter, and our volume is 8 milliliters. So the milliliters will cancel, and we get that the max mass of the block can be is 8 grams before it starts sinking. Okay, so the pressure is defined as the force over the area. So this would be the units for pressure. A force is a newton, and an area could be a meter squared. So you could see a newtons per meter squared as a pressure, which is equal to a Pascal as PA. Another common unit of pressure is ATM, atmospheric pressure, and atmospheric pressure is 1 ATM at sea level, so that's why ATM is used a lot. But it's a force over an area. Okay, and so like let's say you had a cylinder that's sitting on like a surface, then this cylinder would apply force on this part where it's touching the table here. So this part where it's contacting is going to have some area, and there's also going to be a force pushing down, which is the gravitational force. That's what this table is feeling. So in this case, it would be the mass of the cylinder times gravity over the area, the cross-sectional area that's at the contact point. Okay, and so let's do an example where we find pressure for force over area, and then we'll talk about how to find pressures of fluids. Okay, so we have a 60 kilogram person stands on the ground with his sneakers and in heels. The area of one sneaker is this, the area of one heel is this. What is the pressure exerted by the person in each case? Okay, so let's write out what we got. We know the mass of the person is just 60 kilograms. Okay, so now we need to know the area. So the area of one sneaker is 0.025 meters squared, and the area of one heel is 0.003 meters squared. Okay, so if we have our person here, and they're standing on the ground, there's two contact points with the ground. There's the two different feet, which we can assume is equally distributed in mass. So this person obviously has an FG, so that's the force that's causing this pressure, and the area is the area under their feet. Okay, so the pressure is going to equal Fg over the area. And so we can look at our two different scenarios. Let's look at the pressure when they're wearing sneakers first. So Fg is going to be mass times gravity, and we're given the mass. And now the area, since there's two sneakers on the ground that are equal, will be double the area of one sneaker, so 2 area of the sneaker. And so now we have all these variables, and we can go ahead and plug these in and get the pressure exerted when wearing sneakers. So this is 0.205 or 0.025. And so this will be 11760 pascals. Okay? And we're just looking at the pressure exerted by the person, not the total pressure, because we're always feeling a pressure from the atmosphere, and that's what we'll talk about next actually, but this is just the pressure exerted by the person. Okay, so now let's do for the heels, and we'll have the exact same formula except for we want the area of the heel this time, and so we'll get 69.8 2 times the 0.003 area of the heel, and we get 98,000 pascals. So we notice that when wearing heels, it's a much greater pressure than when wearing sneakers, and that's because there's less area. So that's why if you have something that's a lot wider and you feel it on your hand, it doesn't feel as much pressure, but if you have something very thin, you'll feel that more because there's not as much area. Okay. So now let's look at the difference between the gauge pressure and the absolute pressure. So let's say we have some cylinder or cup of a liquid, for example. We're always feeling an atmospheric pressure all around us, which is due to the pressure buildup from the atmosphere. And so that's about 1 atm. and it's 1 atm at sea level. So at the bottom of this cup of liquid, it's also going to feel this atmospheric pressure pushing down on the top of the liquid. But at the bottom, it's also going to feel pressure from the liquid itself, which we can call the gauge pressure. So if we were saying how much pressure did the liquid cause, it would be the gauge pressure at the bottom. And these two pressures added together, we define as the absolute pressure. So that's just the pressure that it actually feels at some point. And so this can be applied to like a tank as well, and we'll do some examples. But this gauge pressure of the fluid itself can also be represented as the density times gravity times height. So how do we get this equation? So let's say we have this cup of liquid that has a density rho, right? We know that pressure equals the force over the area. So in this case, the force is this Fg due to the liquid. Okay, so it's still going to be the mass times gravity over the area. But we need to get what is the mass of this liquid. Well, we know, like let's say it's like a cylinder, for example, that the volume in this cylinder or container is going to be the area times the height, because this is the height, and then the bottom also has some area. And so if we multiply these together, we get the volume. Okay? And if we use our density equation of mass over volume equals density, we can get that volume equals the mass over the density. So we can plug that in and get mass over density equals area times the height. And so the mass is equal to rho area over height. And so now what we can do is come in here and plug it into this equation and get pressure equals rho area height times gravity over the area. And so the areas will cancel and we get the pressure is equal to rho gh. And so that's how we derive this equation. So this works for a fluid in a container. Okay? And so now let's do some examples comparing the atmosphere and gauge and absolute pressures. So we see at sea level the atmospheric pressure is 1 atm. Find the gauge and or absolute pressure of these scenarios. So first we have a tank that's left open. So in this case we just have a tank and it's open to the air. So the absolute pressure is just going to be what's felt everywhere, which is the atmospheric pressure, which in this case is 1 atm. And so the gauge pressure, we don't have anything in this container, it's only felt the atmosphere, and we can also write the gauge pressure as the absolute pressure minus the atmospheric pressure, which in this case there's 1 absolute minus 1 atm, which equals 0. And so since there's nothing new, the gauge pressure will simply be 0. Okay, so now we have a sealed tank with an absolute pressure of 1 atm. So in this case we have a tank, but this time it's sealed off and we have 1 atm of pressure inside. So we already know the absolute is 1 atm, that's what we were given. So what is this gauge pressure? Well, we can use this exact same equation up here. The gauge equals absolute minus atm. Atm still equals 1, so the gauge pressure in this case is also going to be 0. Just because it's sealed, it still has the same pressure inside as outside. Outside also has 1 atm. That's like if you had a water bottle, you opened it up, and then you closed it. The water bottle has the same pressure inside as we do on the air outside. So it's the same amount of pressure, so the gauge pressure is 0. So now we have a sealed tank with an absolute pressure of 0.5 atm. So now we have a tank, and there's only 0.5 atm of pressure in here. But outside there's still 1 atm. So we know the absolute pressure is equal to 1 atm. And so we can use our equation, and the absolute is still, or this should not be 1, this should be 0.5. The atmospheric pressure is still 1, but the absolute pressure is 0.5. That's what they told us. So it's 0.5 absolute minus the 1 from the atmosphere, which means we a negative 0.5 atm of gauge pressure, which sometimes they will say like 0.5 atm of vacuum. So if you like started pulling air out, now there's less pressure inside here than outside, then the gauge pressure is negative relative to the atmosphere pressure. So now we have a sealed tank with a gauge pressure of 1 atm. So in this scenario, the sealed tank, we don't know what the total pressure is, but we know the gauge pressure is 1 atm. So we can think about it, let's say we had 1 atm outside, and let's say this is the gas molecules from outside, and we seal the tank. When we initially seal it, we know the gauge pressure is 0, that's what we saw up here. But now it's 1 atm, so we added some gas or maybe we changed the volume, but somehow we changed it so that now the gauge pressure is 1 atm, which means it's larger than the outside, so the total pressure had to go up, so our P absolute will be equal to 2 atm. And we could also use that P absolute equals the atmospheric pressure plus the gauge pressure, and we would get 2 from that as well. Okay, so let's do one final example where we look at this pressure due to a fluid. So it says, what is the gauge and absolute pressure at the bottom of a graduated cylinder filled with water to a height of 0.1 meters? Okay, so we have let's say we have like the ground and there's a cylinder, and it's filled up 0.1 meters. So we know that the pressure is going to equal, we know the gauge pressure first is going to be the gauge pressure from this fluid, which is the density times gravity times height. So something to notice here is that the pressure caused from a fluid has only has to do with the height and does not have to do with the area, which is why you might see pressure expressed as a height of fluid. So you could actually say this gauge pressure is equal to 0.1 meters of water, and that would be a unit of pressure. And so you might see like millimeters of mercury as a pressure is a common one that is used. So you could even say 0.1 meters of water and you're done. But in this case we're going to find it in pascals, because when we find the total pressure we'll want to use pascals or atm or stuff like that. Okay, so let's find the gauge pressure using this rho GH first. So the density of water we know it's 1 gram per milliliter, and it's also, if we just convert, is 1,000 kilograms per meter cubed. Okay, that's the density of water. Usually that'll be given in a reference or something, or you'll have to convert it from a different density of water that you already knew. Okay, gravity is 9.8 meters per second squared, and the height is 0.1 meters. And so I'll write the units out so that we can make sure that we have a unit that we know. So our gauge pressure here, if once we type that all in, is 980. And so if we combine our units, we get kilograms, and we'll cancel 1 meter out, and we get kilograms meters per second squared per meter squared. And so this top part is just a Newton per meter squared, so this is in pascals. So we're good. Okay, and so if we want to, so this is the gauge pressure in pascals. Now the reason we found it in pascals is so that we could find this absolute pressure, and we know that the absolute pressure is just equal to the gauge pressure plus this atmospheric pressure. And so the PATM is just 1 ATM, and 1 ATM is about 1 times 10 to the 5 pascals. It's more like 1.01, but for this we'll just use 1. Okay, so now all we have to do to find the absolute pressure is just add the 980 plus the 1 times 10 to the 5. And so we get 100,980 pascals. So an interesting note about this example is that we can see that due to the liquid, it only caused 980 pascals, but the atmospheric pressure that we're always feeling is 100,000 pascals. So the total pressure is only going up by a very small amount compared to what it already was. And so it shows how there is a lot of pressure always being felt. And so the height of a liquid doesn't give that much pressure when it's only a small amount. It takes a lot of liquid to apply the same amount of pressure as the atmospheric pressure. So the buoyant force is the force that you feel when you're in the water pushing you upwards. And it equals the density of the fluid that you're in, the volume that you displace, and the gravity. And so let's say we had a cup of water, or just some fluid, and there was a ball inside. So this ball is going to feel force due to gravity, because obviously gravity is acting on it, and also this force buoyant. So in this case, the volume of the fluid that this ball is displacing is equal just to the volume of the ball, because all of it's in the water, or whatever fluid it is. But now let's say we had another scenario where the ball is floating at the top here. Now there's still some gravitational force on this ball here, and there's still buoyant force, because otherwise, without the buoyant force, the ball would just be falling through, but the buoyant force keeps it at the top. But in this case, there is still some volume that's displaced from the water, but it's less than the full volume of the ball, because only about half of it looks like, in this case, is being displaced. So when you're using this volume right here, you want to make sure that you use the volume that's actually being displaced by the object, not just the volume of the object. Unless the whole thing is submerged, then you can use the whole volume. Okay, so let's look at an example. So a marble is placed in a cup of water. The water is then poured out and replaced with a liquid that is 1/3 as dense as the water. The marble remains at the bottom of the cup. Compare the buoyant forces that the marble felt in each scenario. So let's say we have a cup here, right, and there's a marble at the bottom. And then we have a second cup, and scenario 2 where the marble is still at the bottom. Now, the first one, we just have water, which we can call a density of rho, and then we pour it out, and the liquid is 1/3 as dense as water. So in this case, we can say it's 1/3 rho. So we know that the buoyant force equals the density of the fluid, the volume times the gravity. Okay, now in this case, since the marble is fully submerged, the volume that's being displaced is equal to the volume of the ball. So we can just use volume of the ball. Okay, and since it's fully submerged, it's not going to change between the two scenarios. So let's write a formula for the first scenario. We'll just say force 1 is the density times the volume times gravity. And now when we replace the fluid with the 1/3 density fluid for force 2, we get 1/3 the density, volume, gravity. And since these variables right here are not changing, we can say that the force 2 that is felt is 1/3 the force that is felt in the first scenario. And so that's what we get. So we would have in both these scenarios a force due to gravity and a buoyant force. And in this one, there's less buoyant force. And that'll be less buoyant force. And then so obviously, since the marble's standing on the ground, there's also going to be a normal force, because the forces have to balance since the object is not moving and it's not going through the container. So let's start with volumetric flow rate. So the rate that something flows through a pipe is the change in volume. So the change in that volume is equal to the area times the velocity of that fluid. So let's look at a pipe that, say, a liquid might be flowing through. So there's some area to this pipe, and it's flowing at some velocity. And so that will give you your volumetric flow rate. Okay, and now let's say the pipe gets smaller and the area now goes to this area. Well, if we have a constant volumetric flow rate, then this velocity must get faster because there's less room for the same amount of volume that flows in this first point to flow in the second point. And so that's where we get this equation, where really what we're saying is the volumetric flow rate is constant. So if we had the area and the velocity, and one of those changes, the other variable must change with it. And then finally we have this Bernoulli's equation that basically is energy for fluids, is how you can think about it. So first off, we just have our pressure. So this is our initial pressure at the initial point, and the pressure on this side is just the final pressure, the pressure at the end point. And these, you may notice, look very similar to potential and kinetic energies. So this is kind of like the potential energy of your fluid, and this is like your initial kinetic energy, because we are using this height variable to determine potential energy and the velocity to be the final, or to be the kinetic energy. And so this will be your potential energy final, and this will be your kinetic energy final. And we'll do an example later using this equation. Okay, but let's do an example with changing areas first. So we have water flows through a 0.05 radius pipe at 0.05 meters cubed per second. The pipe then gets bigger to a radius of 0.1 meters. What is the change in velocity? So let's draw out what we're looking at here. So we have the pipe is going through like this originally, and then it gets wider. So we know that the volumetric flow rate is going to be 0.05 meters cubed per second. And so when you're pumping water through this pipe, just because it gets bigger doesn't mean that the same amount of volume isn't going to be going through at any time. Okay, so we have this constant volumetric flow rate. And so now we also know that the radiuses are changing. So the first radius is going to be equal to, and I'll write it as R naught, equals 0.05 meters, and the final radius is 0.1 meters. And so we need to compare these velocities. So let's start by just finding the initial velocity, and we can do the same to find the final, or we can use that other equation. We'll do it both ways and show that it's basically just doing the same thing. So this volumetric flow rate, which I'll call V dot, is equal to the area times this velocity initial. Okay, and this will be the initial area. So to find this area, we can use the radius. So let's rearrange it for the velocity, which is just this volumetric flow rate over the area initial. And so we were given this flow rate of 0.05 meters cubed per second. And the area is just going to be, we're assuming this is a circular pipe since it gave us a radius, is just pi r squared. So we can do pi times the initial radius, which is 0.05 squared, and that's in meters. And so the meters will cancel, and we'll get 6.37 meters per second. And so that's our initial velocity. Now to find our final velocity, we can do this exact same thing, and then we can use the other equation. So I'll do this exact same thing actually, and then show that the other equation works. And it works because we have this constant flow rate. So we can find the V final in the same way of having this constant volumetric flow rate and our area final, which is going to be still 0.05 meters cubed per second over our final area, which is pi r squared, but we want the final rate, which is 0.1 meters. And so when we plug that in, we get 0.016 meters per second. And so if we were to do it the other way, we also know that if we have an area 1 velocity 1 equals the area 2 velocity 2, we could have found this velocity final by doing area 1 velocity 1 over the area 2. And so if we plug those in, we would have pi the initial radius, which is 0.05 squared, times this velocity of 6.37, which we found, over the 0.1 radius squared times pi. And so these pi's cancel, and if we plug it in, we will also get 0.016 meters per second. So we could do it using this equation or using this constant flow rate. And so now we just need to find the change in velocity, which just is the velocity final minus velocity initial. So this velocity is getting smaller since the pipe is getting larger. And so we get a change in velocity of negative 6.35 meters per second. And that'll be our final answer. Alright. Now let's try to derive Torricelli's theorem. And I think Torricelli is how you say his name. Torricelli, if you're watching, I apologize if I said it wrong. So Torricelli's theorem is basically relating the height of a tank to the velocity that a fluid would be flowing out given that there's like a small hole or opening. So we're going to use this Bernoulli's equation here, where we have the pressure initial plus the density gravity initial, or density gravity times height initial, plus 1/2 rho v naught initial, equals this final pressure plus rho g h final plus 1/2 rho v f squared. Okay. And so we can cancel out some variables. First off, the pressure is going to be constant at the input and output because we have this P naught that's pushing down at the top of this tank, and we also have P naught, the same P naught, pushing in on this gap here. So these pressures are going to be equal, so those cancel. Now we also need to set our relative height. So if we set this height equal to 0, we can say that at this point height is 0. So at the final point where the liquid is leaving, the height equals 0, so we can cancel out this final height, and so the initial height is what this h is saying right here. So really we should just say h equals 0 at the exit point, because if we set h to be 0 at the bottom, then we would have to deal with the heights of both of these. But to make it easier, since we're dealing with energy, we can set that to be our reference point. And then finally, the velocity of the fluid up here at the top is going to be about 0 because we're looking at this constant height and this constant velocity, because if we have a big tank and a small opening, compared to this velocity it's going to be insignificantly small, so it'll be about 0, so we can cancel out this initial velocity. And so now we're just left with the rho g h equals the 1/2 rho vf squared. And so these densities cancel, and we can divide or multiply by 2 to get 2gh equals this velocity squared. And so the velocity of the small opening is the square root of 2gh, and that will be our equation for velocity. So now all we need is the height of the tank relative to the exit point to find what the velocity of the fluid would be exiting. And we use this energy equation to solve for that. Alright, that's all of Unit 8 and the last unit for AP Physics 1. So make sure you go back and watch any other sections that you're still confused about, leave any questions in the comments, and thanks for watching.